Okay, good morning again. So yesterday I talked a lot about the exascale from the high performance computing side, from the scientific computing side. So today I'll try to focus a little bit on the big data side. And this is a project we started around like 2.5 years back compared to the MPI project, which I mentioned yesterday. It was like a 15 years old project. So we tried to take a lot of ideas from there, okay, saying that if we can accelerate scientific computing, why can't we accelerate big data? So that will be the focus of the talk. Now, as many of us have been knowing, I mean, the big data has been exploding. We have all these different characteristics of the big data. People have been exploring all these different directions. But if you take a look at, let's say, the typical multi-tier data center architectures and where these components are being used, so broadly, you can divide them into two categories. Like in the front end here, you will try to see like components like Memcached or the MySQL, HBase, they are being used. And on the back end, data analytics might be the SDFS, MapReduce, Spark. So these are the kind of two broad categories of middleware which are being used. Now on the Apache Hadoop side, I mean, that has been in the field for many years. And of course, in the earlier days, it used to be the Hadoop 1.x, where MapReduce is combined with the resource management and data processing. Since 2 years back, now the Hadoop 2.x has come, which actually decouples so that you can have the MapReduce and the resource management in a decoupled manner, and that provides flexibility to run it on different environments. Now, some of you must have also heard of the Spark. So that is the new middleware in the town, which tries to provide an in-memory data processing, especially for iterative machine learning jobs and to provide some interactive data analytics. It is a new kind of a design using like Scala, some resilient distributed data sets. It performs some MapReduce-like software operations. It also interfaces with the HDFS, that is the Hadoop distributed file system on the back end. Now in all these stacks, as we'll try to go on, we'll see that most of these designs have been done with sockets-based communication. So if you come to the network layer, it is the standard sockets, TCP/IP. That's what works in these default designs. Then the other one I mentioned about this is the Memcached. The Memcached is, again, very extensively being used in the multi-tier data centers on the Web 2.0. The common example I give, you can correlate to it. Let's say you are trying to do some flight search on Orbis, okay? I'm sure many of you would have done. Look for some prices, let's say from San Francisco to New York. You will see some very good pricing. Then you would like to buy it, and as soon as you click it, the message comes out saying, sorry, that fare is not there, right? How many of you have seen these kind of messages, okay? So there could be two reasons. Either really that fare is not there. That is one reason. The tickets have been sold. But the other one, which is most probable, is what you are seeing from the first time when you ask the query, the response came from something which was cached there from the previous queries. And that's what many of these middle tiers, they try to do, because typically if you see your user pattern, like how many times you search and how many times you actually purchase, it is not one-to-one, right? Most of the time you like search for like 10 times, different pricing, different routes, then purchase one. So they want to have the rate, the transactions rate quite high, so they are caching the results of the previous queries and the results of the API call so that to give you very good fast user response. And of course, if you are trying to buy it, it goes back to the database and then gets the latest value and then actually performs the transactions. So this is a good model. So what it tries to do is, like if you see here in this tier, like from the Memcached servers, it actually takes memory from all these nodes and try to put a big aggregated cache. That's why the name comes the Memcached kind of things. And of course, the larger you can have it, you will be able to get very good performance. So it is a scalable model. But again, at the same time, it is very network intensive. And the default designs, again, use sockets at the networking layer. Okay? So in that kind of a context, like if some of you are in the room know like the very, like go back in the MPI world, 15 years back, 20 years back, again, it was running with sockets. But then once all these newer networking technologies came, like the Miricom came, the Quadrix came, then InfiniBand came. So a lot of these designs started moving and trying to see how we can exploit the modern networking technologies so that we can accelerate this operation. So exactly we took the same view, saying these are the middlewares now using sockets now, and can we accelerate? So that will be the focus here. So I'll start with some of the challenges here, and then I'll try to introduce the project I mentioned, HIBD, High Performance Big Data, around 2.5 years back. Then I'll try to show you some case studies here. First, I'll start with the case studies with the traditional Hadoop, with different components, how we have accelerated like the SDFS, MapReduce, and Spark. Then the second one, that is a new trend is coming. People want to use MapReduce only with HPC cluster. I mean, there are so many HPC clusters with Lustre. So you don't have to really go through SDFS. You can try to use the default MapReduce, but want to with the Lustre. So there we want to explore how we can accelerate that. And the third one I'll try to show, this is a very recent designs we have done, especially SDFS. There are a lot of bottlenecks. Now, can we actually try to have some kind of a heterogeneous and in-memory capability so that the data can be located in the RAM disk as well as SSDs, hard disk, or even Lustre in a very flexible manner. And that I'll try to show you that you get orders of magnitude benefits. If you go through like this, there's an enhanced SDFS design. And then I'll talk a little bit about the RDMA-based designs for the Memcached and HBase. And then I'll also try to stress about the role of the designing benchmarks. Okay? Like this field, we'll see that, I mean, the workloads are so different. All different companies, they have a lot of internal things, unlike scientific computing, where a lot of things are open. Here, not many things are open. So one has to actually, when you are trying to design this kind of systems, you need to see what kind of benchmarks you need to validate and how you can design those benchmarks. So this is the slide I showed yesterday. I mean, this shows like how the HPC field is moving. Of course, we have, these are the technology advancements, multi-core and many-core technologies and accelerators, especially this RDMA-based networking, whether you think of like InfiniBand or Rocky and the SSDs, and now the NVRAM is coming, and we have these accelerators. So this is a dense chart, but if some of you are familiar with the Open Fabrics, that is the consortium which is trying to work together with all these different networks and protocols. There are a lot of these kind of protocols are available, and mostly on the left-hand side, this is the traditional sockets-based design. That means if you have any applications or middleware, and you are not changing, they are written with sockets, so they can run with the traditional gigi or 10 gigi, 40 gigi, 100 gigi infrastructure. If they have the TCP offload engine, they can also run there. And also InfiniBand has a mode, the emulation mode of the TCP IP called IP over IP. So that means you are not changing any of your application or middleware, and they can run in all these environments. But what leads to this high performance is this side, which the InfiniBand introduced this RDMA. But the main thing is that you need to modify your middleware or application. Instead of sockets, you need to move to the verbs. Okay? I mean, that's what like MPI stacks have done over the years, or parallel file systems. So all these stacks, once you modify to the verbs, then you can take advantage of all the user space. It can run with the InfiniBand adapter, InfiniBand switches, etc. Okay? So the question is, who does that? I mean, that's what if the middleware needs to be modified, then of course your end application doesn't have to be modified. Okay? An example like an MPI library we have modified, but MPI application you don't have to modify. It can just run on its own. So that's what I'll try to show. Our approach is to move from this side to this side for these big data middleware. And this is just the fact, like you can see the RDMA technology has been widely adopted, not only for MPI, but for all these parallel file systems. We are getting all these less than 1 microsecond latency, 100 gigabits per second bandwidth, 5 to 10% CPU utilization, and also excellent scalability. So in that context, if you ask the question, how do we proceed to design the next generation, like the communication and I/O libraries for the big data systems, this is how you'll come up with a picture. Okay? So at the bottommost, we have different networking technologies, the commodity multi-core and many-core architecture, the storage technologies. And then, of course, here these are the big data applications and benchmark, and they are running with the middleware like the SDFS, MapReduce, HBase, Spark, or Memcached, and this is where they are running with sockets. Okay? And then inside this, of course, you have to handle all these different kinds of point-to-point communication, threaded models, synchronization, I/O file system, QoS, virtualization, and fault tolerance. So when we started looking at this, so the first thing we wanted to ask that these are written with sockets, can we start using RDMA protocols here? And that's what the initial set of results I'll try to show what we have done in the last 2.5 years. But then the question comes that once you make, like these middlewares have been designed several years back, assuming network is slow. Okay? And now if you can accelerate the network portion, then that opens up a lot of other opportunities that we can revisit those architecture at the upper layer, which could not be done earlier, and then you can again get more benefits. And we have not done all those things, so there is a lot of things can be done in the future to bring both these things together. So what I'll try to focus on at a very abstracted point of view, if you see, like let's say the big data applications are written currently with sockets, they're running with the Ethernet network, and especially the sockets are not designed for high performance. So the question is, can we have some of these designs so that they can directly run with verbs? Okay? So that is a very simplified view of what we are trying to do. And if it can directly run with the verbs, then of course, all your other components can directly run and then get the benefits, and we want to see how much benefit you can get. So this is where like let me introduce the HIBD project. So if you just go to this site, it has a lot of information. So over the years, just like our MPI project, once we have the designs and we have the publications, we have been trying to push it into the community. So you should be able to actually download these RDMA-enabled versions for Hadoop 2.x, 1.x. We also have an RDMA for Memcached, and also there is gradually we have started pushing some of these HIBD benchmarks. It is picking up traction. Currently around 88 organizations from 18 countries are using this. Last week we crossed more than like 2,500 downloads here. And we are in the pipeline to bring out like the RDMA-based design for Spark and HBase, et cetera. They will be coming out soon. So just to see, like, let's say, think of just the RDMA for Apache Hadoop distribution. So we have both for 1.x and 2.x. And the 2.x is based on 2.50. And in another 2 to 3 weeks, we are trying to push out the version for 2.60, which is the latest version in the Apache Hadoop. So what this does, that internally it has RDMA-enabled designs for HDFS, MapReduce, and RPC, and they have been all integrated together. Okay? And it's very easily reconfigurable. You can run it over InfiniBand, you can run it on Rocky, or even the traditional sockets model. So whatever numbers I'll try to show, you should be able to actually validate all those things. If you have an IB cluster or a Rocky cluster, just deploy, and you should be able to do it with very simple changes in the configuration files. And while trying to do the design, we actually don't change any of the APIs or upper layers. Okay, so that means it's compliant. So if your job is running with Apache Hadoop 2.5, this version will run without any changes. Okay, so we are not changing anything into the bigger infrastructure. So as of now, this is like an integrated software stack, but we have been getting a lot of requests to make it available as a plugin. And that's what is in our next few months. You might try to see the plugin so that it can actually run with, let's say, Cloudera distribution. It can run with Hortonworks or any other Hadoop distribution. It should be able to run. But so far, it is not available. You just have to download this complete thing and should be able to run it. The same thing we have done for the Memcached. This is again based on this. The current release is based on the Memcached 1.420, Memcached 1.018. And the concept is very similar. We keep the API compliant, so you should be able to install it on your system and should be able to run your Memcached applications on top of it. And then this is the benchmark which is publicly out now. Is the Memcached, different kinds of benchmarks like set, get, mix, these kind of things, so that you can try to evaluate some of this performance of your RDMA-based design compared to the standard sockets-based design. So let me go into some of the details and try to show how we have done it, and then what are the kind of numbers we get. So I'll try to touch base on SDFS design, MapReduce design, and Spark in an isolated manner, like only focusing on SDFS, then MapReduce, Spark. Of course, the release has all these things being put together. So think of like this is the how to accelerate the SDFS. So if you see the SDFS, the way it is written, or the way it works, replication. So for every data block, you have to make certain number of replication, and the default is 3. And this is where actually you spend the most of the time, okay, the replication. So this is the part, the right part. What we have done is, this is like the Java native interface. So this is where we have done our design, which directly, instead of going through the standard sockets interface, it goes over the verbs interface so that it can actually run it with the RDMA-enabled network. And of course, we only optimize the critical data path. There are the other communication paths which are just going through which are not critical. We have not changed those things. So they still go over the sockets. Then of course we have parallel replication support, some on-demand connection kind of things to make it much more efficient. So this design actually, we presented at Supercomputing 2012. And then the second generation design we presented last year at the HPDC. So the latest release has the second generation design. So here it shows, like, let's say, very simple, like how much time you save in the communication time. So here, like, this is the x-axis is the file size, and this is the communication time. What we are trying to show is the 10 gig. And then on these two things are the InfiniBand QDR. But here we are running IP over IB. That is the IP over IB emulation. And then this is the RDMA design. Okay. So of course, there are two different networks here. But with the InfiniBand network, we'll try to focus on what you can get by default with the sockets or the IP over IB, and what you can get with the RDMA-based design. So here you will see that around like a 10 gigabytes file size, you can actually cut down your communication time by 30%. So we are not changing any hardware between this InfiniBand. It's just the RDMA-based design is trying to give you these benefits. So here, this is the number we have run a little bit larger scale. This has run on the TACC-Stampede system. So it uses FDR. And here we are running on 64 data nodes, around 1,000 cores. And here you can see that we can push the throughput by around 64% and reduce the latency by around 37%. Now, similar kind of things we have done also for the MapReduce. So not only we have enhanced the RDMA part on the shuffle stage, but here also we have brought out a lot of like in-memory merge. And also we have carried out some advanced overlapping, because with RDMA-based design, your communication costs change. And by taking advantage of that, we are able to efficiently optimize all these maps, shuffle, merge, and reduce these different stages, so that as a system, you should be able to get much more benefit. And here are some numbers here. This is the SORT and TeraSort numbers. And here we are trying to show, these are all InfiniBand QDR, and this is the IP over IB. This is our RDMA-based design. Here also we are trying to show the UDA design, which is available from Mellanox, the unstructured data accelerator thing. So everything is running on the same system. And here we are trying to show, like for example, like 240 gigabytes of SORT with 512 cores, we see around like 40% improvement. And this is around like, again, on a 64 nodes, 320 gigabytes of SORT, we get around like 38% improvement. And this is another workload from Purdue. If some of you are not familiar, this is called Purdue workload. Just like in the MPI world, some of you might have known about NAS parallel benchmark, like NPB, which brings different kinds of kernels into a set of benchmarks. So same thing these people have done. So they have different kinds of things like adjacency list, self-join, sequence count, word count, invert index. They try to reflect different kinds of behaviors of the big data applications or kernels. And of course, wherever there is more communication, we see the benefits. So here, let's say the self-join, we see around 50% improvement. Here, sequence count, we see around 49% improvement. So then we started this work trying to take the similar kind of designs to Spark. And we presented this, we presented this in the last year's Hot Interconnect conference here. So this also takes similar kind of like RDMA-based shuffle, some new designs like SCADA-based plugins, dynamic connection management. And if we see some numbers here, we see like, let's say this is a common benchmark for evaluating the Spark, which is called group by. And here we see around like an 80% improvement or 20% improvement. Okay? So this is still being worked out. We have not pushed it. The Hadoop side has been pushed, but this is the Spark RDMA-based design, which will be pushed next. So now let me change the gear a little bit. As I said, this is the traditional Apache Hadoop, where people want to use the HDFS. But as a lot of HPC clusters with Lustre kind of file systems are there, then people are trying to explore how we take advantage of these infrastructures for pure MapReduce applications. Okay? And so here, if you see, there's the standard any HPC systems. We have the Lustre deployment. Then you can actually run your mapper, reducer. So there are different ways you can actually utilize. So for example, let's say the local disk where you put the intermediate data, like once the mappers generate the thing, you have different choices, like whether you put it in the local disk or you can use it in the Lustre. So what we have done here is we try to provide you a lot of flexibility in the software stack so that we have, let's say, these are the mappers. They are trying to push the data through the Lustre. Then these are the reducers. You can do Lustre read or RDMA. So we provide Lustre-based shuffle or RDMA-based shuffle, or even you can do hybrid. You can also do dynamic stuff, trying to see which shuffle approach tries to do you the best. And also you can do, like, let's say, in-memory merging and overlapping. So these are some numbers with local disk being used as the intermediate data directory. This is taken from the TACC-Stampede. So if you see like a 0.5 terabytes of sort in 64 nodes, we can give you like a 44% improvement. Compared to the standard sockets-based design, that's the vanilla one. With RDMA-based design, you should be able to get a lot of benefits here. And similar kind of things happen here for 640 gigabytes of sort in 128 nodes, you get around 48%. So this is the data taken from SDSC-Gordon. That is also another HPC system with a lot of SSDs. So there you will see that the Lustre is used as the intermediate data directory, not the local disk. So here you see around like 34% improvement and 25% improvement. Then the next one, what we are working on through this our experience, we saw that the HDFS has some of the bottlenecks. So now the question is, can we try to provide a lot of flexibility so that the HDFS can take advantage of either RAM disk or SSD or hard disk or Lustre, and in a very flexible manner. And that's what we have done here. And different kinds of policies are there to utilize these heterogeneous storage devices, different kinds of eviction and promotion schemes. You can do some hybrid replication. We'll be actually presenting this paper at the CC Grid conference in May. But here, if you see the numbers with the new design, so let's say here, this is the IP over IP design. This is the new design with the RDMA. You get almost factor of improvement, like a factor of 7, factor of 2 improvement, not just percentage, okay? Because we are trying to leverage the in-memory aspect here. And similarly, kind of a random writer, you see around like a 3x improvement. And here it shows some initial numbers again on the SDSC-Gordon. This is the default HDFS. Then this is the Lustre. And this is the new design, which is trying to even, compared to both of the approaches, it tries to deliver the best. And of course, there are some different trade-offs on the storage space. Because HDFS, you are making like, let's say, default 3 replication. Lustre is only 1 replication. Here we use 2 replication. Like keep something in the memory and something on the storage to get the best performance, and with the trade-off with the storage space. So similar kind of things we have done for the Memcached side. Here the Memcached, because we are dealing with like outside clients, you need to make sure that whether your clients are also RDMA enabled or not. Okay, so for that we have a flexible design. Like we have like verse worker thread or sockets worker thread. So if the client is not enabled with the RDMA, so they go to the directly sockets. Otherwise, it is the verse enable worker threads they work. So this is an experiment we carried out on the TACC-Stampede, and we have gone up to like 4,000 clients. So think of like a Memcached, which is taking a big amount of memory up to from 4,000 clients, and that's the huge Memcached we are working. And here, if you see like on this system, like a Memcached gate latency 4 bytes or even 2 kilobytes, we can reduce the latency by a factor of 20. So that means the user should be able to see very fast response from this RDMA-based design, and then the aggregated throughput we are able to push almost by a factor of 2. And the HBase design is very similar to HBase. And here also we see like this is the Yahoo Cloud Service benchmark. This is like the 10 gig number. This is the IP over IP number, and this is the This is the RDMA-based design. Here also we see around like 40% or 42%. And as I said, like this design has not yet been pushed, but that's what will be coming out soon. Now, while we tried to do all these kind of designs, what we found out that not only like we have just touched a little bit of these, and as we saw, like we have enabled the RDMA protocol, we of course have to take a lot of look at the upper level changes. But the bigger thing what we saw when you are trying to work in some part, let's say SDFS part only, or MapReduce part, or RPC part, there is no systematic way to see how do you proceed with the designs, okay? If you think of like the Apache Hadoop, always like people just run short or TeraSort. These are very high level applications. You can always make some changes, but you don't know whether you are benefiting or whether you're hurting with any designs, and which design is leading to the benefits, which component in the design to be changed, so that in the community, there is no real low-level benchmarks. And this is nothing new. I mean, we have seen this when we started our MPI project. Yesterday I mentioned like 15 years back. The same thing happened. Like you try to bring some new MPI features. First of all, people don't know how to use it. And the second thing is how can they exactly measure the performance? So this is where we have started this thing called OSU MPI Micro-Benchmarks over the years. It has gathered a lot of momentum. So every time we add some new features, we also release the benchmark so that people can actually do the evaluation. So this is exactly what we are trying to do here. If you see, like these are the current benchmarks. At the lower level, there are no benchmarks to guide the design. And not only that, there is also no correlation to see which design should be able to guide you to the next level of the best designs. So along this line, so what we have done is like, let's say, these are like standalone SDFS benchmarks. For example, just evaluating the SDFS, if you want to try out different kinds of architectural changes, these are like sequential write latency, read latency. You can modify a lot of these parameters. That is like purely for SDFS. Similar kind of things what we have done also for RPC. Similar kind of things we have done for MapReduce. The MapReduce currently, if you see, most of the things like DFSIO and all those are benchmarks are there, then it tries to bring the SDFS. Okay? So just MapReduce, there is no benchmark as such, and here we have actually provided some newer benchmarks which you can just use to change the number of mappers, reducers, intermediate supple data patterns, supple data sizes to evaluate just the MapReduce component. So we are actively working along this direction, and these benchmarks like gradually you will be seeing which will be released to the community so that you people can also try to evaluate it in the same manner. So our future plans here, as I indicated, like our next goal is to have this Spark and HBase and have these plugin-based designs available so that it can work with other distros, and also like the Lustre-based design, and this is the enhanced HDFS design. And we'll try to push the OSU micro-benchmarks. But at the same time, I think there are a lot of opportunities to go and look at these upper-level architectures. And because now the network has become faster, we have accelerated, so we should be able to make some changes to the upper layers to even get the benefits in a higher manner. So let me conclude here. What I tried to provide is like an overview of the big data processing middleware, provided an overview of the cluster technologies, discussed the challenges, and presented some of the initial designs, how you can take advantage of these to accelerate these components and the challenges in designing the benchmarks. But again, this is a field which just, there are a lot of opportunities. And also we heard from the previous speaker, that means many times you can take a look at these problems and then see, I mean, think of it in a little bit different manner and you will have newer kinds of solutions. And that's what we want to do so that we can actually come up with better designs and so that the next generation big data analytics can be done in a much more faster and scalable manner. So with this, again, I always try to show all my past and current students who have actually contributed to all these things. I just come and give the talk here. With this, let me conclude. And again, those who joined late, just go to this site. I mean, these are all publicly released stacks, so you should be able to just download and play with it. And if you have any questions, I'll be happy to take a few questions now. Otherwise, we can talk offline.